Okay, so today's lesson is on naming and drawing alkyne hydrocarbons. So these alkynes are one of those what we call unsaturated hydrocarbons. So these are the hydrocarbons that contain triple bonds, and in fact we're actually going to see that these may also contain double bonds, but the fact that they contain a triple bond is what classifies them as alkynes. So alkyne hydrocarbon compounds contain at least one triple bond between the C. It's not shown here, it's just a hyphen, but really what we're looking for is a carbon molecule triple bonded to another carbon molecule. And this is the what's really important to identify. Okay? So make sure that you identify a triple bond within the carbon chain between two carbons. So at least as long as you have one triple bond between the carbons, you have what we call an alkyne hydrocarbon. When naming, okay, the ending is YNE. Okay, so we've looked at things like ethane as the alkane. We've got the ethene, right, with a double bond, and now we'll have an ethyne as the triple bond. Now, when numbering the carbons, double bonds take precedence over the triple bond. So even though we've got a triple bond in our chain, right, the double bond is what's going to take priority when we go about naming it. Now, the general mathematical formula is as follows. Very similar. So we've looked at the alkanes. The formula for the regular chemical formula was CN H2N plus 2. For the alkenes, with the double bond, one double bond, we have CnH2n. Now, with the alkyne, what we're doing by adding that extra bond between the double bond, right, changing an alkene to an alkyne, we are now taking away two more hydrogens. So notice, as we go from a single carbon-carbon bond, which have the ability to bond to 3 hydrogens each, we go to a double bond that now have 2 hydrogens, and then we go to a triple bond, which allow us only 1 hydrogen on either end, or 1 bond on either end. So notice now, if we were trying to write out a chemical formula for the following, notice how we go, and each single time that we move from an alkane to an alkene, we subtract 2 hydrogens from the actual chemical formula. And then when we move from the alkene to the alkyne, we are subtracting 2 more hydrogens from this expression. Okay? Now, alkanes, carbons, all single bonds end in A-N-E. Alkenes, carbon with at least 1 double bond, and it ends in E-N-E. And today's lesson, which is on the alkynes, carbon with at least 1 triple bond. Right? So there's a possibility of a double bond also, and actually, oops, there's a typo here. It doesn't end in A-N-E, it actually ends in Y-N-E. Now, alkynes are even more reactive than alkenes. So it goes as follows. Alkynes, most reactive, are greater in terms of reactivity than the alkenes, but the alkenes are more reactive than the alkanes. So we can say that the alkanes are the least reactive of these hydrocarbons. So the minute we add a double bond, it becomes more reactive. The minute we add a triple bond, it's even more reactive. So triple bonds represent a linear arrangement. Therefore, they do not need to worry about stereoisomerism. Cis and trans, I will be putting a video on cis and trans, and we're looking at the geometric shapes. We should know, if we're putting together models that are linear, with single bonds, we can rearrange this where we can kind of orient this carbon here in a different geometric pattern. But with triple bonds, right? Triple bonds, and if we look at the simplest of all the triple bonds, and this is the ethynes, right? Where we have, so we think of monkeys eat. So 2 carbons, and there's a triple bond with them, and then there'll be just the 1 hydrogen on either end. So this will be a linear arrangement. And it's best to show this if you had the ball and stick model kit and put that together, put your 2 carbons together, put the triple bond, show the triple bond between the carbons, and note where you're placing the hydrogens, and you'll see that it will be a linear arrangement. Now, when naming and drawing alkynes, use the same rules as those used for naming alkenes, with the exception, okay, of the fact that we identify the double bond first. If there is a carbon double bond, and we might also have a triple bond, right? So this is considered an alkyne, right, with a double bond, right, with the alkene double bond in the format. But we'll see in a couple of examples closer to the end when we get to the sample problems. Now, remember to count the carbon bonds very carefully, right? Remember, as we said with the alkene, if we do have a double bond, we start counting the carbons from the carbon closest to that double bond. Now, let's look at this sample problem. Name the following compound. So what we want to do is we want to try to find the longest possible chain, but because we've got this triple bond here, that longest chain must include this triple bond. So longest chain, for argument's sake, make it nice and simple, will be that. So we look at the carbons, and we've got 1 carbon, 2 carbons, 3 carbons, 4, 5. So we know we've got 5 carbons, so it's part of the pentane derivative. But because we've got this triple bond here, this pentane becomes a pentyne. Now, where is the location of this pentyne? Well, it's between the 2 and 3, so it's always the lowest of the 2 numbers. So it's a 2 pentene, meaning that pentyne. So knowing that this triple bond is located on the 2nd carbon. So now, if we look at our branch, we've got a branch here of a 1 carbon branch. So this 1 carbon represents a methyl group. So we've got a methyl group. Where is methyl group located? It's located on the 4th carbon. So when we put this all together, the name is a 4-methyl 2-pentyne. So notice, 2-pentyne, meaning the triple bond is on the number 2 carbon. There are 5 carbons in our main chain, right, with the triple bond located on the 2nd carbon. And we've got a methyl group, 1 methyl group, located on the 4th carbon of this main chain. So we've got another sample problem here. Name the following compound. So take a moment and just break it down, because there's a different way of writing the name of this one, because the biggest thing that a lot of students are going to panic is, well, we've got this double bond in here, and we've got this triple bond. So what do we do? Okay. So take a moment and just break down what's the main chain and number your carbons and try to figure out some of the different groups. So, now, let's look. The main chain, for argument's sake, we will use this one here right in the middle. Nice and simple. Now, which end are we going to label our carbons from? Now, we've got this double bond here. So we're going to number it two ways. Start from here. 1, 2, 3, 4, 5, 6, 7 carbons. Let's name it. So now, if we number it like this, remember, the double bonds, okay, the double bonds take precedence over the triple bonds. So we want to number it in a way where the double bond will have the lowest number. So the lowest number here, this double bond is between 3 and 4. So we know that if we number it this way, the double bond is on the 3 carbon. Now let's number it the other way. Right? So 1, 2, 3, 4, 5, 6, 7 carbons. Right? So if we number it this way, this double bond now is located between the 4 and 5, which means the double bond is now on the 4th carbon. So the first time we were correct with our numbering. So we don't number it that way, right? We number it the first way. So we know we've got a 7 carbons. So we know we've got our derivative, which is a heptane. But now here's the problem. We've got a heptane, right, derivative. But we've got a double bond that turns it into a heptene. But we also have a triple bond that names this a heptyne. So so what do we do when we go about naming this? Well, let's put that off to a side for now. Let's look at the chains that we've got. So we've got one chain here on the number 2 carbon. We've got another chain here on the number 4 carbon. So right now we've got a 2, a 4 hyphen. They're both methyls, so we've got 2 methyls, so we've got a dimethyl group. Right? We've got a dimethyl group, and the one thing that is common from this main chain is the hept. So we've got a something hept group. Now, here is the thing. This is how you label the remaining parts. Where is the location of the double bond? The double bond is located on the 3 carbon, right? The triple bond is between 5 and 6, so it's on the 5 bond. So this is how we name it. The common part of the chain is that it's a hept, meaning 7 carbons. So now, remember, double bond takes precedence. So the remaining part of the name would be, we want to include the 3 in here, because in the 3 carbon, we have the ene group, the double bond, right? Let me just erase this here so we can fit it. And then, on the 5 carbon, we have the ine group. Okay? So be really, really careful. These ones can get really messy when you're putting them together and trying to write them out. Okay? So this is how it's written. We're part of the 7 carbon chain. We've got 2 methyls located on the 2 and the 4. And now, how do we rewrite the rest? Well, we've got to show ene, and we've got to show ine. Right? We do it in alphabetical order. Right? The ene first, and then the ine. And then this number here is just going to tell us what carbon is this double bond located. What carbon is this triple bond located? So the name, just for argument's sake, let's just clean it up here and show it to you. It's a 2,4 dimethyl hept, 3 ene, 5 ine. So if you have to go back, rewatch this scene again, because like I said, this can get really tricky when you're going about naming, but remember that part of this main part here, we've got the hept, the 7 carbons. And then it's after that it's a number, remember hyphen, the double bond, hyphen, between numbers and letters, right? So notice we use commas when we're writing number to number, and anytime we're writing a number to a letter, we are always separating it with a hyphen. So on the 5 carbon, we've got our triple bond. On our 3 carbon, we've got our double bond. 7 carbons in total, 2 methyls, 1 located on the 2 carbon, another one on the 4 carbon. Like I said, take a moment, look it over, and double check that you are correct and that you understand this question. Drawing alkyne, same rules as the alkenes. Number the carbon starting from the carbon closest to the triple bond in the main chain. Right? Of course, it's closest to the double bond if there is a double bond. Okay. Now, keep an eye out for double bonds, as I said, as they take precedence over triple bonds when numbering the carbons. Be careful to ensure that each carbon only has 4 bonds associated with it. Count your bonds very carefully. It's really important because you want to be able to identify where are the other hydrogens. Okay, so let's look at the following sample problem. Draw a condensed, right? We don't want to show all the hydrogen bonds. Draw a condensed structural diagram for the compound 4,5-dimethyl 2-heptyne. Take a moment. Try this out. Okay, so now, hopefully, you've gotten this. You'll get the same answer that I'm going to get. So the first thing we want to do is start off with the main chain, heptyne. So we know we've got to have 7 carbons. So 1, 2, 3, 4, 5, 6, 7. Right? So we're going to number it also as such. 1, 2, 3, 4, 5, 6, 7 carbons. Now, we need to put in our double bond, and our double bond is located on the number 2 carbon. Right? So on the number 2, and it's always between the 2 and the next number. Okay? So it's on the 2 carbon, our double bond, which means now, because there are no other double bonds, we can just put single bonds in all of it, with all of them. Okay? So now, we've got on the 4 carbon and on the 5 carbon, 2 methyl groups, right? So on the 4 carbon and on the 5 carbon, we've got a methyl group, right? So with these methyl groups, it's CH3 to the outside, right? Because that carbon is bonded once, so it has room for 3 more. So now let's go in and draw in. So we've drawn everything that we need. Now the only thing that's missing is in this condensed diagram, right, are the hydrogens. So if we look at carbon number 1, it's got 1 bond, which means it has room for 3 hydrogens. The number 2 carbon here is bonded 3 times, which means it has room only for 1 hydrogen. Let's look at the number 3 carbon. Also has 3 bonds associated. It has room only for 1 more hydrogen. Remember, each carbon can fit up to 4 bonds. Right? That's how you can tell how many hydrogens you have left. So let's look at number 4. The number 4 carbon also has 3 bonds. So it has room for a 4th bond to a hydrogen. Number 5, same thing. 3 bonds, has room for 1 more hydrogen, 1 more bond. Carbon number 6 has 2 bonds, so it has room for 2 more hydrogens. And the last one has only 1 bond. It has room for 3 hydrogens. So here is the condensed structural diagram for a 4,5-dimethyl 2-heptyne. Okay, so always do a double check. Go back, see if you can identify your diagram and get the original answer. All right, so do the steps. So go backwards to do your own little self-check. So here's our here's one more example. I think we have one more after this. Draw a condensed structural diagram for the compound 3-ethyl 4-methyl 1-hexyne. So take a moment, try this one out, and see if you're going to get my answer. So let's start off with our main chain. It's a hexyne. So we know we're going to have 6 carbons. 1, 2, 3, 4, 5, 6 carbons. Now we've got a hexyne, so we know we have a triple bond. Where is it located? On the number 1 carbon. So let's number our carbons. 1, 2, 3, 4, 5, 6. Remember, we number them any way we want because we're drawing them in the way we're going to label it, right? So we know we've got a 1 on the 1 carbon. We've got our triple bond. So now, because we've already done our triple bond, now we can just throw in our single bonds between the other carbons. Now, let's do the other groups. We've got on the 3 carbon, an ethyl group. So we're on the 3 carbon, an ethyl group, and an ethyl group has 2 carbons associated with it. On the 4 carbon, we have a methyl group. So it's a 1 carbon, right? So now let's figure out how many hydrogens on this ethyl group. Well, this carbon here has already 2 bonds on either end, so it has room for 2 hydrogens. This outside hydrogen, room for 3. Same thing with this methyl group, 3 hydrogens. So now let's figure out how many hydrogens we can fit with the remaining, or with our main chain. So carbon number 1 here has carbon bonded 3 times, so it has room for 1H. The next carbon has 4 bonds to it. It has no more room for any more H's. Okay. Carbon number 3 has 3 bonds, has room for 1 more H. Carbon 4, 3 bonds, it has room 1 more H. Carbon number 5 has 2 bonds, so it has room for 2 hydrogens. And the last carbon, carbon number 6, has 1 bond, so it has room for 3 hydrogens. And here you have the example. Here's your condensed structural diagram of a 3-ethyl, 4-methyl, 1-hexyne. So let's look at this last sample problem. Draw a condensed structural diagram for the compound 2-methyl-pent, 1-ene, 3-ine. So take a moment, try this one out. This is one of the tricky ones that I said, right? So break it down, figure out how many carbons is the main chain, where are my triple bonds, my double bonds, because I have now a double bond to show and a triple bond, as well as my methyl group. So take a moment, work this one out, see if your answer comes out to the same as mine. So, first things first, we always want to know how many carbons in our main chain. How many carbons in the main chain? It's a pent group. So we know we're going to have 5 carbons. 1, 2, 3, 4, 5 carbons. Okay, so let's number them. 1, 2, 3, 4, 5. Now, next thing. We've got a 1-ene, right? So that 1-ene means I have a double bond on the number 1 carbon. So we've got the number 1 carbon, a double bond. We've got a 3-ine, which means I've got a triple bond on the number 3 carbon. So here's my number 3 carbon, and it's between the 3 and 4, I've got my triple bond. So once I've done my double bonds and triple bonds, now I can just come in and put in my single bonds. Next step, we've got a 2-methyl group. So on the number 2 carbon, we've got our methyl group. 1 carbon that's bonded to 3 hydrogens. Last step, pretty much we're almost done. All we gotta do is write in our hydrogens. So let's look at this carbon number 1. Carbon number 1 has 2 bonds, has room for 2 hydrogens. Our carbon number 2 has 4 bonds, no more room. Right? Our carbon number 3 also has 4 bonds, no more room. Our number 4 carbon also has 4 bonds, no more room. Our number 5 carbon has 1 bond and room for 3 more hydrogens. So be really, really careful with your hydrogens. No, we didn't put very many hydrogens because these double and triple bonds that are in the middle chain, part of the chain, really take up a lot of the carbon's valence electrons. Remember, carbon has 4 valence electrons, capable of 4 bonds to form around carbon. Right? And so if these double bonds and these other branches, they all take up part of those bonds. So which means they will not have hydrogens associated with them.